Oh, what's up? It came to my knowledge that you like some scientific stuff. So I have one to you. How airplanes can fly. And another thing, why I always spill my water when I try to put inside a cup. Let me help you. That's the Coandă effect. But what is the Coandă effect? Well, it's the tendency that a fluid has to follow a curved surface, like the wings of an airplane or the border of your cup. Let me show you how.
Well, so to show you how it works, I will first show you how it would work with a spoon. You can see that when the curved surface of the spoon touches the water tends to attach to the surface and follow its shapes. With the cup is the same. The water tends to follow the shape of the border of the cup because it's curved.
Okay, now that you saw how it works, I will propose a new thing. How it would work with a spherical surface. If we tie this ball with a string and put some degrees increasing the water flow, we will see a different way of the Coandă effect. The Coandă effect is related with the viscosity of a fluid. The higher the viscosity, the stronger the Coandă effect.
So our question is about how much the flow of the water affects the Coandă effect. And here's the idea that my friends and I bring to you. Attach the ball with a string with a holder, an universal holder. And also to help us with the instability of the jet of water, we use a diffuser of water that in Brazil we call it aerador japonês, something like Japanese aerator. And to make it happen, we put the ball into the flux of water, and while it was into it, we start to pull the set. What happens is that we were increasing the angle, and in that way, we would be able to see how much the flux of water could be able to hold the ball. And I also like to remember you all that while we were doing this action, the Coandă effect was present. We can see the Coandă effect in the way that the fluid, in this case the water, attaches to the surface of the sphere, the ball that we are using. Also, here's the why the ball stays inside the flux. We have attraction force called T, a vertical weight force called P, and the force caused by the Coandă effect, denoted by Fc. So, decomposing the weight force, we obtain a force orthogonal to the traction force called Pt, which is in equilibrium with T, since the ball does not move vertically. In addition, we have the Px component, which is nothing more than a force orthogonal to the force of Coandă effect, that in equilibrium situation is counterbalanced by the same force. And here's some data. We made 8 measurements, and if you look at the very end of the curve, you can see that it starts to stay straight. And this is the limit, because the angle starts to be so wide that the flux of water cannot hold anymore. And this is why, at some point, the ball escaped the flux of water.
A curiosity, the Coandă effect is used to improve the aerodynamics of airplanes as well the aerodynamics of Formula 1 cars. Go Ferrari!